This next chapter will look at the properties of lipids. Lipids are compounds that can be extracted from cells by nonpolar organic solvents. Okay, this is the one characteristic they have in common. They are not necessarily all, in fact, they're not all structurally similar, but there's various classes of lipids. Complex lipids are those that are easily hydrolyzed. These include long-chain esters, which are called fatty acids. Complex lipids also consist of waxes. Simple lipids are not easily hydrolyzed in acid or base. These include such things as steroids, prostaglandins, and terpenes. Okay, so here we have some examples of complex and simple lipids. This is an example of a fat. This is tristearin. It has 3 ester groups. And then here we have acetyl palmitate, which is a wax. And then these compounds over here are simple lipids because they lack the ester group and they're not easily hydrolyzable. Waxes are esters, and they have a long chain fatty acid and a long chain alcohol group, and both of these chains are straight. Some of the common examples that are found in nature: spermaceti, which is found in the head of the sperm whale. Beeswax is a mixture of waxes, hydrocarbons, and alcohols that bees use to make their honeycomb. Carnauba wax is a mixture of waxes of high molecular weight. Carnauba wax comes from a tropical plant, and some of the uses of carnauba wax are in shining the finish on cars and also waterproofing surfboards. Okay, so here we have a component of beeswax, one of the compounds that's likely to be found in beeswax. You have a very long chain carboxylic acid part and a long chain alcohol part. Fatty acids are unbranched carboxylic acids, usually with 12 to 20 carbons. Most contain an even number of carbons because they are built up biosynthetically by acetic acid. Melting points will increase with increasing molecular weight. Unsaturation, especially if you have a cis double bond, greatly lowers the melting point. Fatty acid esters of the triol glycerol are called glycerides, or sometimes called triglycerides. Triglycerides are the most common glycerides, and they are used for long-term energy storage in both plants and animals. Fats are solids at room temperature. Most are derived from mammals. These include such things as butter, lard, beef tallow, and even palm and coconut oil. Even though they're called oils, they're solids at room temperature. Oils are liquid at room temperature. Most are derived from plants or cold-blooded animals, such as fish. Okay, so here we have a table of various fatty acids. And we can see that for the saturated fatty acids, the melting point goes up as the number of carbons increases. These are all solids at room temperature. Unsaturated acids, especially those with cis double bonds, many of these are liquids at room temperature. Okay, here we have oleic acid. This is a major component of olive oil. Okay, it melts at 4 degrees. And as we increase the number of cis double bonds, the melting point continues to decrease. Okay, notice here that these double bonds are not conjugated. Here's a fatty acid with trans double bonds, and you can see that it would be a solid at room temperature. Arachidonic acid is a starting material for the biosynthesis of many compounds such as cholesterol and other steroids. Okay, so these are referred to as saturated fatty acids. These are unsaturated fatty acids. Trans fats, those with trans double bonds, are typically those that occur as a result of hydrogenation of oils. And most nutritionists agree that trans fats are not healthy. They're not easily digestible. Okay, another term you may be familiar with is omega-3 fatty acids. Since omega is the last letter of the Greek alphabet, if we count back 3 carbons from the end, we have a double bond. So linolenic acid is an example of an omega-3. Okay, so here is stearic acid. The chain is flexible, but on average, you can see that it has a straight or linear shape. Here is oleic acid with a cis double bond. Now, the cis double bond introduces a sharp bend in the chain, and that significantly lowers the melting point, and that is because the molecules of oleic acid don't pack together as efficiently as, say, stearic acid. The trans double bond has less of an effect, and we actually saw this in the previous slide. Okay, so here's a fully saturated fat and one that contains unsaturated fatty acids. And you should be able to tell that the saturated fat, being more compact, can pack together much better in a solid. Okay, because of the sharp elbow bends in the unsaturated fat, okay, these can't get as close together as the saturated fats, and so these unsaturated fats are usually liquids at room temperature. Saponification is the making of soap. We talked about this back in our chapter on carboxylic acid derivatives. Today's saponification refers to basic hydrolysis of any ester. We take a fat or oil and we heat it with an excess of sodium hydroxide and water. This causes the ester groups to break down, and we obtain glycerol, and then we obtain the sodium salts of the various fatty acids. Now, these triglycerides don't necessarily all have the same ester group, the same carboxylic acid making up the ester. You can make soap from a variety of different fats and oils. Corn oil, coconut oil, sunflower oil. You can make it from animal fat. You can make it from fish oil. We actually tried that one time. It does make soap, but it smells horrible. This is a process that's been known for probably at least 3,000 years. The ancient Greeks and Romans made soap using either animal fat or olive oil. Okay, so how does soap work? Okay, so here we have a fatty acid carboxylate salt, and most of the chain is nonpolar, greasy, hydrophobic, whereas the head is charged, it's ionic. When soap is used to clean up dirt and grease, what it does it'll disperse the grease into tiny droplets called micelles, and the soap molecules will stick their tails into the grease droplets, and the outer surface then is surrounded by these charged ionic groups. And then the grease is emulsified and can be washed away. These micelles are actually pretty small. They may contain only about 80 to 120 soap molecules. So in water, soap forms a cloudy solution of micelles with the hydrophobic heads in contact with the water and the hydrophobic tails clustered into the interior. Sodium ions, not shown, are dissolved in the water surrounding the micelle. Here we have some synthetic detergents. Detergents generally operate on the same principle as soap, particularly something like sodium dodecyl sulfate, sodium lauryl sulfate. The difference is that we have a sulfate instead of a carboxylate. Sodium lauryl sulfate is used in detergents. It's a major component of shampoo. Okay, one of the advantages of sodium lauryl sulfate over soaps is that if there are certain metal ions present, and there typically are calcium and magnesium ions present in municipal tap water, these will precipitate the soap molecules, and this produces something called soap scum. Sodium lauryl sulfate will not precipitate in the presence of most metal ions, such as calcium and magnesium. If you wash your hair with ordinary soap, over time it leaves a dull film because of the soap scum. And so that's why you want to use shampoo detergent instead. Okay, here we have an example of a cationic detergent. Cationic detergents are typically quaternary ammonium salts, and some of these have germicidal properties. Others are used in fabric softeners, for example. Okay, what they do is they will help neutralize the charge from the use of anionic detergents and therefore prevent static electricity. Nonoxynol is an example of what's called a non-ionic detergent. It's water soluble. It contains these multiple ether groups and then an alcohol group on the end. Because of the multiple ether groups, it can hydrogen bond with water. This is a contraceptive. And then here we have a carboxylate salt. This is Gardol, which is typically used in toothpaste. Phospholipids have, in some ways, similar properties to soap, except they have two hydrophobic tails and a charged group, namely the phosphate and the amine salt group here at one end. Okay, the phosphate might have an additional alcohol attached by an ester linkage, which is what we have here. Okay, so here is a phosphatidic acid in its ionized form. And okay, you can see we've got the polar head and then we've got two nonpolar tails. Okay, these phospholipids are what make up the lipid bilayer of cells. Okay, so the interior and the exterior and interior have hydrophilic surfaces, whereas the interior of this bilayer is hydrophobic. So these phosphoglycerides can aggregate into a bilayer membrane with polar heads exposed to the aqueous solution and the hydrocarbon tails protected within. These lipid bilayers are important parts of the cell membrane. They can restrict the flow of water and dissolve substances. Okay, next we'll turn to a different class of lipids. These are the steroids. This is the steroid structure. Consists of 3 6-membered rings and a 5-membered ring in this arrangement. Usually the rings are all trans. There are some rare exceptions, but usually these rings are trans to each other. Many of these steroids will contain either a carbonyl or an OH, and often a side chain at C17. And they may contain double bonds. Okay, so here is decolon, which is 2 fused cyclohexane rings. Okay, here's the trans and here's the cis. Mostly in steroids, it's going to be the trans. Okay, so here we have, here's trans and here's cis. Okay, a little bit different shape. And if there is a cis, it's usually between the A and B ring. Okay, one important steroid is cholesterol. It is a common biological intermediate. It's probably a precursor for other steroids. There's a side chain at C17, which is right here, and then we have a double bond between 5 and 6. Cholesterol also serves as an insulating material. It's a waxy, water-insoluble substance, insulating material around brain and nerve cells, and it provides a little bit of rigidity to cell membranes. Gallstones are almost entirely cholesterol. The sex hormones, testosterone and estradiol, are steroids. Okay, the difference here, the female hormone has an aromatic ring and one less methyl group. Testosterone is converted to estradiol in the ovaries. Okay, these are some other examples of steroids. Cortisol is a major natural hormone of the adrenal complex. Fluoquinone, acetonide, is more potent for treating skin inflammation. And this last one is for treating asthma. Okay, the next class of lipids we'll look at are the prostaglandins. These are very powerful regulators. In fact, they're more powerful than steroids. They consist of a cyclopentane ring with two long side chains trans to each other. Most of these will have 20 carbons. They're derived from arachidonic acid. Okay, remember that was the fatty acid that had the 4 cis double bonds. Okay, some of the things that they can regulate include blood pressure, blood clotting, allergic response, digestive activity, labor onset. The biosynthesis of prostaglandins begins with an enzyme-catalyzed oxidative cyclization of arachidonic acid. Okay, these prostaglandins will have various letters and numbers which indicate double bonds and functional groups and so on. For example, here's PGE1, and this explains what all that means. I don't necessarily expect you to remember these letter and number designations. So prostaglandins serve a variety of regulatory functions. Some of them reduce inflammation, some of them cause inflammation, and some of the pain-relieving drugs, such as aspirin and ibuprofen, operate by inhibiting an enzyme called cyclooxygenase, which is involved in the synthesis of inflammatory prostaglandins. Okay, next we'll turn to terpenes. These are composed of 5-carbon isopentyl or isoprene groups, and they are isolated from the essential oils of plants. Many of them have either a pleasant taste or fragrant aroma, and often they're used in flavorings. Examples include anise oil, bay leaves, and here are some others. Some other essential oils. Turpentine from evergreens, oil of celery, and these are some of the major components. Carvone is extracted from caraway seed. The enantiomer is found in spearmint oil. There's myrcene from bay leaves, and then cedar leaf oil, alpha-pinene. Okay, so this is the building block of terpenes. It's isoprene, 2-methyl-1,3-butadiene. And terpenes are composed of 2 or more isoprene units. Okay, if we look here, okay, here's one isoprene unit, here's another. Okay, so here's myrcene, beta-celanine, which is from celery. There's another isoprene unit, and there's the third. Terpenes are classified by the number of carbons they contain in groups of 10. Okay, so a monoterpene has 10 carbons, or 2 isoprene units. A sesquiterpene, sesqui means 1.5, has 15 carbons. Diterpene has 20. Okay, so here is squalene. Squalene is a compound that's been isolated from shark liver oil, and squalene is a starting material for the biosynthesis of cholesterol.